In this video, we take a look at finding the derivative of a product and a quotient of two functions and what we call the product and quotient rules. And then we'll round things off by looking at higher order derivatives. So far, we've only taken the first derivative. Can we take a second derivative, a third, and so on? And we'll develop a notation for that. So in the last video, we were able to find formulas all through the limit definition of the derivative. We were able to find formulas for the derivative of a constant, derivative of x to a power, derivative of a constant times a function that's differentiable, and the derivative of the sum or difference of two functions, right? So those all had nice formulas. And kind of the next logical step is to take a look at the derivative of a product of two functions. Okay? So what we get is what we call the product rule. The product of two differentiable functions, f and g, is itself differentiable. And it goes just like this. Unfortunately, we'd love for it to be f prime times g prime. That's just not the case. We do, however, have a nice little formula. Again, this comes from the limit definition. We see that the derivative of f times g is just f times g prime of x plus g times f prime of x. Okay, so there's just this little, combination type pattern that we see. We take the derivative of one of the product pieces, and then we leave the other piece alone. And then we switch. We add to that the derivative of the other function times the, original g of x then. I often think about this like the first function and the second function. So I'll take the derivative of the second function while leaving the first function alone, and then switch. Okay. So I wanna go through a couple examples with this. Once you get the hang of it, it's really not so bad. And the nice thing is that because there's a plus sign in between those two terms, that the order doesn't really matter. I can switch them and remember them pretty much in either direction, right? It doesn't matter. So what I want to do here is I want to show the product rule works by taking the derivative of this function here, 3x minus 2x squared times 5 plus 4x. Okay, so I'm going to take this derivative two ways, of course, one with the product rule, and then the other by just rewriting this function and actually just multiplying everything out, foiling, and then taking a derivative, and just show that the derivative isn't different by using two different methods there. Okay, so my product rule tells me that my derivative should be I've got two functions here, first and second, f and g. So I'm going to read right from my formula there. I take f of x in green, multiply by the derivative, and I'm going to write it just kind of how I would read it, the derivative of g, 5 plus 4x, okay? Plus the second function, 5 plus 4x, times the derivative of the first. Okay? So after you do a couple of these, you'll be able to kind of take those derivatives in real time, but I've written them with that ddx notation. That's implying that I still have to actually take a derivative, okay? But I want you to see where those parts are coming from, so try to relate that up to what I have in pink at the top. Actually taking my derivatives now, I'm going to keep what I have in green there. Derivative of 5 plus 4x should just be a 4. Plus, and again, what I have in blue stays the same, times the derivative of 3x minus 2x squared should be a 3 minus 4x. And I'm just going to simplify this, multiply everything out and collect like terms. I see that the 4 distributes, and then this guy all foils here. I end up with 12x minus 8x squared plus a 15 minus 20x plus 12x minus a 16x squared. Okay? So once I combine like terms, I've got x squared terms, I've got x terms, and I've got one constant term. So this all simplifies and combines to be minus 24x squared plus 4x plus 15. Okay, so there's the derivative, there's y prime. I want to verify that this makes sense. So there's my product rule. I want to verify that this derivative is the same by looking at what I get without the product rule. Okay, so if I multiply those two functions out, f and g, what I get is minus 8x cubed plus 2x squared plus 15x. Okay, so you can FOIL that out and check my work there, but that's what the function is. That's y. So then y prime, or the derivative of that trinomial, that third degree polynomial, just with my power rule, should be negative derivative of minus 8x cubed is minus 24x squared, plus the derivative of 2x squared is a 4x, plus the derivative of 15x should be a 15. So I've got exactly what I had on the previous page there. So I've got combined knowledge here. I've got what I've known from before with my power rule, and also what I know with now the product rule. Okay, let's do another example. And this is really where the product rule is kind of going to shine and where it's pretty much required. So I want the derivative of x e to the x. I don't have any choice but to use product rule here. I've got two functions that are totally different that I can't really rewrite to take a derivative a different way. So when I go to my derivative here, I've got the product rule says first times the derivative of the second plus the second function, e to the x, times the derivative of the first. Okay? And again, I've written it kind of how I would read it. Still have yet to take those actual derivatives inside. So you get some weird kind of terminology going. The overall derivative that I'm taking contains smaller derivatives within it, if that makes any sense. So my derivative then, derivative of x e to the x, I can write as x times the derivative of e to the x is just e to the x, plus the other e to the x there times the derivative of x is just a 1. Okay? And again, after you do a couple of these, you'll be able to jump right to that line that I just wrote without kind of writing everything out, slowly the first way. But I suggest it while you're learning the formula for product rule. Okay? And then just a little simplification, I see there's an e to the x in common that I'm going to factor out. So what I have left is e to the x times x plus 1. So not so bad. It's really a rather friendly formula. So I want to keep doing some examples here, bring in some other components, some of the other rules that we've seen already. Find the derivative for y equals 2x cosine x minus 2 sine x. Okay? So what I want you to note here is that I got two separate terms, and the first term, I definitely see two different functions, right? I've got like a 2x and a cosine x, okay? So that guy is definitely going to require product rule. So I start my product rule for that first term, not the whole I will take the derivative of the entire function, right? But in that, I've got product rule of that first term. So the first function, 2x, times the derivative of the second function, cosine x, plus the second function, cosine, times the derivative of the first function, derivative of 2x. Okay? This I'm going to subtract afterwards the derivative of 2 sine x, but I don't need product rule here, right? I don't have two separate functions of x. I just have 2 times sine. That's a constant multiple. That 2 is multiplying my sine. So that's just really 2 times the derivative of sine of x, right? I would take that as I would, from before without knowing the product rule, right? So don't kind of use that product rule there. You don't need to with the 2. Simplifying my derivatives there in the first term, I've got the derivative of cosine is minus sine, the derivative of 2x is 2, and the derivative of sine is cosine. Okay? Just a little bit of simplification here. I notice that 2 times cosine minus 2 times cosine, those guys are going to disappear. And I'm just left with minus 2x sine x. Okay? So it just so happened that after I took a derivative of some of the pieces parts there, I ended up with something that disappeared. Doesn't happen all the time, but thankfully we lost a term. Makes things a little bit nicer. So again, don't create product rules where they don't exist or where they're not needed. It'll take some time, but you'll get a feel for when I absolutely need power or product rule and when I don't. we're now ready to look at the quotient rule. Okay, so product rule, it's pretty straightforward. Everything comes from that formula. Quotient rule is very similar, and there's also kind of similar techniques to when I need quotient rule and when I don't. So I'll try to accent that just a little bit as I go. And what we have here is the derivative of f of x divided by g of x. If I've got a quotient, two functions that are one divided by another, and I want the derivative, it goes just like this. And it's a similar kind of setup to the product rule, but it's not the same. But it also comes from the limit definition. What we have is a big old fraction here, and it goes like this. The bottom, the denominator, g of x, times the derivative of the numerator, minus the numerator times the derivative of the denominator. That's all in the big numerator, divided by g of x squared. Okay? Like I said, it's not exactly obvious why the formula is that, but it comes from the limit definition. That proof is, you can find it easily online or in the textbook, I believe. So I want to use this. I'm going to use this quotient rule here, and I'm going to try to color code things with blue and green so that I have a better idea of where each piece is coming from. If I want to take of course, since I'm dividing by g of x, then I have to say that g of x cannot be 0. Okay? That's just a little aside, but it is important. I can't divide by 0 there. Given some function, f of x is 5x minus 2 divided by x squared plus 1, I want to find f prime of x. Okay, I'm going to take the derivative of this quotient, and I've got two functions. I've kind of double used f of x there, so forgive me for that. I've got abusing some notation. But in the numerator, I've got a function of x. Denominator is a different function of x. So to take the derivative of that, I definitely need the quotient rule. Okay. So my derivative, I'm going to handle like this. I've got a big division, and I write g of x, the denominator, times the derivative of the numerator, minus the numerator times the derivative of the denominator, all divided by the denominator squared. So I went through that very quickly. You might want to slow it down or kind of take things step by step, write it out beforehand, and then go back and press play. But basically following just as the formula is there and trying to match my colors. Again, I've written it long ways. Just what I mean by that is I didn't take the derivatives in blue and green there in real time. I'm just setting it up so I see where everything comes from. Okay? So what I've got here is a derivative. X squared plus 1 stays the same, but the derivative of 5x minus 2 is just a 5. Minus, again in green, I stay the same there, 5x minus 2. Now the derivative of x squared plus 1 is a 2x. Easy enough. Denominator stays the exact same. Okay? It's tempting to actually FOIL out that denominator. I'm always going to have a g of x squared down there, but you do not need to FOIL that denominator. You don't need to. It usually doesn't give you anything extra or nice that you wouldn't have without expanding it. So my advice is just to leave it the same and don't worry about it. Okay, this simplifies a bit. I leave the denominator alone, and I'm just going to FOIL everything out here. When I distribute that 5, I've got a 5x squared plus 5. And then I'm going to distribute again over here a negative and a 2x. I get a negative 10x squared plus 4x. So I just have two terms that I can combine there, a 5x squared minus 10x squared. So my derivative should be a minus 5x squared plus 4x plus 5. And there's my derivative with the quotient rule. Okay? And that's really all there is to it. That's really all there is to it. So I've got this formula. It's similar to product rule. Again, I'm looking for functions that have a numerator and denominator that are both functions of x that there's no way that I can rewrite to make any better. Let's do another one. I want the derivative of this quotient, 3 minus 1 divided by x in the numerator, gross, divided by x plus 5. Okay? So I want to point some things out here. In the numerator, I've definitely got a function of x, and so in the denominator. So this would imply that I've got quotient rule here. I want you to notice that 1 over x up here, I don't need quotient rule for that guy. So if I were to take the derivative of the numerator, I don't need to do the quotient rule for 1 over x, right? Remember that can easily be rewritten as x to the minus 1, and I can apply power rule there. So just keep that in mind. I don't have to do quotient rule every time I see a quotient. Just be careful, okay? So what I do here, I'm going to take this quotient, and in fact, I'm going to try to make this easier on myself. I start thinking about what it would be to take the quotient rule, yeah? Low d high, bottom times derivative of the top. And the derivative of that numerator is going to give me something a little gross, right? Derivative of 3 is 0 minus the derivative of 1 over x. Well, that's going to be minus 1 over x squared. So I've got fractions inside fractions, which I don't typically like to deal with. So I'm going to try to undo that, or I'm going to try to make it easier on myself. So I'm actually going to kind of try to clear fractions. I'm going to take this and multiply it by 1. And I'm going to do that in such a way so that all the fractions disappear. And that 1 is going to have the shape of x over x. So I'm multiplying through kind of basically by what the common denominator would be in that numerator, if that makes any sense. And what that gives me is a 3x minus 1 over x squared plus 5. This, I can now just go right into taking the, and actually I forgot an x here. I'm going to go right into what would be the quotient rule, okay? From that, when I take the derivative of the original mess, that's going to be the same as taking the derivative of this new expression here. Again, forgot an x. I remember this kind of a different way, right? I remember the formula, of course, but I know it by a little jingle. So I always say this in my head when I'm doing the quotient rule. If I call the denominator low, like the bottom, low, and I call the numerator high, then the quotient rule, the derivative of high divided by low would be low times the derivative of the numerator, low d high, minus is less, high times the derivative of the denominator, d low. Low d high, less high d low, draw a line and square below. Okay, so I always remember quotient rule that way with that little jingle. I don't know why, it just works for me well. So I've kind of stuck to that. I'm going to go through and take my derivative here. So the derivative of 3x minus 1 divided by x squared plus 5x should be low, the denominator, and I need an extra x in there. Sorry, I'm going too fast. Extra x in here. So that's low d high, derivative of the numerator, derivative of 3x minus 1 is 3, less, minus, high, 3x minus 1, d low is 2x, that should be a plus 5 there. 2x plus 5. Okay, denominator squared, that should be an x squared plus 5x squared. Okay, again, just some foiling and simplification here. What happens is I've got distributing everything in, I have 3x squared plus 15x minus 6x, this one's going to be a little tricky, minus 6x, pardon me for just a second, 6x squared, hold on one second, let me let this play, and then I'll get rid of 6x squared plus a negative is minus 13x minus 5 when I FOIL all that out. And that's all divided by x squared plus 5x quantity squared. Okay, So because I left that x out, it kind of messed everything up. I apologize. But here we go. All that's left to do is combine terms in the numerator. So nothing too fancy. I have a 3x squared plus a 2x plus not 15, but a 5. So I got some extra pieces that are going to cancel there. So I believe what I have is a minus 3x squared plus 2x plus 5 divided by x squared plus 5x squared. Okay, so there's my derivative with quotient rule. Take that step by step, piece by piece. Again, I used even a little rewrite before I had to do quotient rule. I couldn't get away from doing quotient rule. Why didn't I just do quotient rule at the start? Again, because I saw that 1 over x in the numerator and knew it was just going to cause issues. I would have had a fraction inside of a fraction again, and it's just difficult to deal with. The algebra becomes more difficult. So I decided to get rid of that to kind of begin with, and then take a derivative to make my life easier. Okay, I want to do another example here. What I was trying to say with product rule, we kind of have the similar thing with quotient rule. We don't always have a quotient, we don't always have to use quotient rule, just really when we can't rewrite. Just when we, have a function of x divided by another function of x, we can't rewrite that, we have to use quotient rule, but sometimes it's beneficial to rewrite things to help us out, right? So it's very common to think, because now I know quotient rule, everything that's a quotient, for example, if I'm taking the derivative of e to the x over 4, I think I have to use quotient rule. Let's just do it to see what happens. I've got low 4 times d high is e to the x, derivative of e to the x is e to the x, less high d low, derivative of the denominator is 0. Derivative of 4 is 0. All divided by the denominator squared. So quotient rule is applicable. I have a quotient, I can do quotient rule, sure. But what happens here, this second term in the numerator is going to disappear, and I've got 4e to the x over 4 squared. 4's are going to cancel, and I've got e to the x over 4. So I've taken some time, I've done quotient rules, things simplified, but I can also just rewrite this as 1/4 times the derivative of e to the x, which is 1/4 e to the x. I get the same thing, right? So what I'm trying to say, again, similar to what I was talking about with product rules, don't make things harder than they have to be, okay? It's very easy because we've got this kind of new knowledge here, and now we think everything is more complicated. It's not necessarily, okay? Do a bunch of examples in different types of these quick derivatives, and you'll get a better feeling for when I absolutely need quotient rule, when I don't, when I need product rule, and when I don't. Okay? So of course, we always try to rewrite to make things easier. Always, always. Let's now figure out what the derivative of tangent of x might be. Okay? And if you know a little bit of trig, we can quickly adjust this to sine of x over cosine of x. I've got a quotient. I can use quotient rule here then to find the derivative. Dy dx is the derivative of tangent of x, which is the derivative of sine of x over cosine of x. So what my quotient rule says is low d high derivative of sine of x less minus high sine of x times d low derivative of cosine of x, all divided by cosine of x squared. Okay, same quotient rule we're friends with. Simplify, or actually go in and then take those derivatives. I've got cosine of x, derivative of sine is cosine, minus sine of x times the derivative of cosine is a minus sine x, all divided by cosine x squared. I'm going through this rather quickly. Feel free to pause along the way, slow it down if you like. Just a little simplifying to do. Cosine times cosine is cosine squared, minus a negative sine times sine is sine squared. All over cosine x squared. And if you remember, cosine squared x plus sine squared x is always equal to 1 from my Pythagorean identity. That's my Pythagorean theorem. 1 over cosine squared. Cosine I can rewrite in the denominator there as secant squared. Okay, that's a reciprocal identity. And what we've got then is that the derivative of tangent of x is just secant squared of x. Okay? So that's one of our other trig functions. That's the third of kind of 6 trig functions now that I can take derivatives of. In fact, because now I know quotient rule, I am able to come up with formulas for secant, cosecant, and cotangent as well. They all require the use of the quotient rule, and I get formulas like this. Derivative of secant is secant x tangent x. Derivative of cotangent x is minus cosecant squared of x, and the derivative of cosecant x is minus cosecant x cotangent x. So these can all be shown with our quotient rule. Okay, well, they're not so bad. Relatively easy derivatives to take. And now we just kind of add those to our repertoire, right? Those are just kind of extra. We now know derivatives of constants, x to a power n, sums and differences, products, quotients, all of our trig functions, and e to the x. Right? We're just going to kind of keep expanding so that we can take derivatives of any type of function. And all along, trying to remember what the derivative actually gives me, slope of a tangent line. Okay, the slope of the curve. A quick example, just revisiting product rule here, y equals x secant x. Okay? So my derivative of this guy, I see 2 different functions multiplied by one another. I've got product rule. So the derivative, y prime, should be the first times the derivative of the second plus the second times the derivative of the first. Okay? Go right to it. Y prime is x derivative of secant is secant x tangent x plus secant times the derivative of x is 1. I don't need to write anything extra there. It's just secant x. Just to simplify a little bit there, secant is a common factor between the 2 terms. I can factor that out. I end up with the derivative to be secant x times x tan x plus 1. Not a bad derivative to take. Pretty straightforward there. So again, practice lots of examples with product and quotient rules. They can be tricky, just depending on the algebra and other things you're working with here. But for the most part, they're just formulas that we kind of have to get used to and try to remember, figure out, when we need product rule and quotient rule, when we don't. So practice. The next thing I want to dive into here is higher order derivatives. Okay. So the idea is here that we can take a first derivative. We've got some notation. Without any derivatives, I've got f of x. Y equals f of x, this function here. The first derivatives I can write as the following, right? So we're pretty used to this by now. I've used most of these notations. That capital D notation I don't typically use, but I've included it here just so you see what happens when I incorporate more derivatives, okay? So basically, when I would go then to take a second derivative, I basically take y prime and prime it. I take a derivative of it. And notationally, all that really gives me, my second derivative is y double prime, f double prime of x, d squared y over dx squared, that's the second derivative, d squared divided by dx squared of f of x, again, second derivative. So that's notation for what we would call a second derivative. And we'll talk a bit in just a minute about where that second derivative might come in and why. And later on in the semester as well, we'll incorporate these second derivatives. We can also write down third derivatives. The prime notation is pretty straightforward, right? I can just keep adding a prime or an apostrophe. The D notations are also pretty straightforward. The power is just going to increase the more derivatives I take. Right? We can keep going. We can keep doing this forever and ever and ever. Eventually, we can kind of just generalize this in sort of the nth derivative, okay? The prime notation gets really cumbersome with n derivatives, right? You can write primes for forever. So the way we handle that is with kind of an exponent. We say y to the nth and f to the nth of x, okay? So those are the nth derivatives of my function. and the other notations just kind of then follow through for exactly what you would expect. Okay? So there's notation for n derivatives, and that, believe it or not, that's something that you'll get into a little bit more in second semester calculus, Calculus 2, but something that you'll explore more. For this semester, we'll basically just focus on the first two derivatives here, because those are the main ones that have significant applications, okay? We'll talk about their meanings more. We've already pretty much discussed the first derivative, right? It's slope of a tangent line. We'll talk about what the second derivative gives us. Actually, in the first case, right now, let's look at some example here. Let's say the position of an object falling on the moon is given by S subscript m, the position on the moon, as a function of t, of time, is minus 0.81 t squared plus 2. So that kind of indicates I've dropped it from a height of 2, an initial height of 2. S here is going to be given in meters, and t is in seconds. And what I'm interested in is finding the acceleration of the object, okay? Acceleration of this object that's falling on the moon. We know from our previous discussion that if I want the velocity of an object, whether it's on Earth or Mars or the moon, I'm looking at the rate of change of position with respect to time. I'm looking at the derivative, the limit as delta t goes to 0, of delta s divided by delta t, the rate of change of position with respect to time. We say s prime. Okay, so that's the first derivative. Acceleration just happens to be the rate of change of velocity with respect to time. How fast is my velocity changing as a function of time? And what that looks like is the limit as delta t goes to 0 of delta v divided by delta t. It's the derivative of velocity, which in fact is really just the derivative with respect to time of position, of derivative of position, the second derivative of position. Okay? So acceleration then is simply the second derivative of position, or the derivative of velocity. Okay? So since I have position, I can then go ahead and find acceleration by taking a derivative, take another derivative then to find acceleration. So I've got an application of the second derivative here. So the second derivative of position is acceleration. Okay? So v would be the derivative of position, is the derivative of this polynomial minus 0.81 t squared plus 2. The derivative, if I bring that 2, the exponent, down and multiply it by 0.81, I've got minus 1.62 t. Subtract 1 from the power, plus the derivative of 2 is 0. To get acceleration from this, I take another derivative. Acceleration is the second derivative, or then the next derivative of minus 1.62 t, which is just a 1.62. Since we've got some physicalness to this problem, it's important to talk about units here. Our velocity is again the change in position. Position here is in meters, and time is in seconds. So it's the rate of change of position with respect to time. That's meters per second. Acceleration is a double kind of unit. It's the rate of change of velocity with respect to time. If velocity is meters per second and I'm changing that with respect to time, then I'm looking at meters per second squared. Okay? So what I've got here is I've got the second derivative of position is acceleration. So I was able to find the acceleration due to gravity on the moon is minus 1.62 meters per second. And just for reference, Earth's acceleration due to gravity is 9.8 meters per second squared. So it's significantly slower, significantly less on the moon than it is on the Earth. And that makes some sense based on what we know with physics. So just to recap, product rule, quotient rule, some new things, but again, don't make things more complicated than they need to be with product and quotient rule. They're required in most situations when you've got products and quotients, right? But there's sometimes when they're not. So have enough confidence in the ability to rewrite functions so you might not have to use product or quotient rule. And then also looking at some higher order derivatives is what we call them, right? So first, second, third, fourth derivatives, so on and so forth. And then just a quick application and a quick use of an actual second derivative where it means something and gives me something. We'll explore second derivatives a bit later in the semester. Other than that, this is all. Thanks for watching.